Now we're gonna do these two problems. For the first one, they want you to find the magnitude of the moments of the f about the x, y, and z axis and solve this problem using a Cartesian vector approach and then using a scalar approach. So for the first one, first we find the points involved. V is a point involved is where the force takes place, and it's this vector right here. And B sits at 4 in the I, plus 3 in the j, minus 2 in the k. And then the Cartesian vector form of the force, which is given at 4 in the I, plus 12 in the j, minus 3 in the k. So, let's start with the scalar approach. The moment about the x, this moment right here, if you're going to do the moment about the x, you need the y and the c components. So, y, fc, and c, fy. And then you do the right-hand rule to find out which one's negative and which one's positive. You know that if you use your right hand and you close your fingers from the y to the c axis, your thumb's going to be aiming in the positive x direction. And that means that the other one's negative. If you use your right hand rule to close your fingers from the C to the Y, your thumb is going to be aiming on the negative x direction. So this one's negative. So then you just replace the numbers. You got a 3, -3, minus -2 times 12, and you get that this is 15 foot-pounds. In the Y, since you're doing the y is x and c, c and x, use your right hand rule. This one will be negative, right hand rule, this one will be positive. So this is -4, -3, -2, and 4. This comes out to be 4 foot-pounds. Alright, and MC, since we're working with the C, we need the X and the Y, and the Y and the X. Now which one's positive, which one's negative? By the right hand rule, this one's positive and the other one has to be negative. When you replace the numbers, you get 4, 12, minus 3 times 4, and this comes out to be 36 foot-pounds. So this is the scalar approach for all three moments, the x, the y, and the c, for this assembly. Now let's do the vector approach. Also known as Cartesian, of course, approach. So the moment about the x is going to be the unit vector in the x times b cross f. Mind you, we found that b is equal to 4 in the I plus 3 in the j minus 2 in the k, and f is given right here. So to build your matrix, on the first row you're going to put the unit vector in the x, which is 1, 0, 0. Here you put b, 4, 3, and -2. And in the last one you put f, which is 4, 12, and -3. So you rerow your first and second column, 1, 0, 4, 3, 4, and 12. You do your positive diagonals, positive, positive, positive. 1 times 3 times -3 is -9. This is 0, this is 0. Now you do your negative diagonals. This is 0, this is negative. 12 times -2 times 1 is positive 24. And -3 times 4 times 0 is 0. So as you can see, this comes out to be 15 foot-pounds, just like our scalar approach right here. So that's good. Now m in the y is u in the y times b cross f. So we build our matrix. U in the y is 0, 1, 0, b is 4, 3, negative 2, and f is 4, 12, negative 3. This is 0, this is 1, this is 4, this is 3, this is 4, this is 12. Just redraw the first and second column. Positive diagonals. 0, 1 times negative 2 times 4 is negative 8. Negative diagonals. Negative, negative, negative. This is 0, this is 0, this is negative. Negative 3 times 4 times 1 is positive 12. Which negative 8 plus 12 is 4 foot-pounds. If we check, our second one was 4 foot-pounds on our scalar approach, so that's also correct. And the last one would be m in the c, which is the unit vector in the c times b cross f. In the first row you put the unit vector in the c, which is 0, 0, 1, then b, 4, 3, negative 2, 4, 12, negative 3. Redraw first and second column, 4, 3, 4, 12, positive diagonals. Positive, positive, positive. First one 0, second one 0, last one is 1 times 4 times 12, that will be 48. Negative diagonals is negative 4 times 3 times 1 is negative 12, and the other two are 0. So this comes out to be 36 foot-pounds. And as you can see, in our scalar approach, it was also 36 foot-pounds. So all the answers should be correct since we got the same answer with both approaches. So the first one around the x is 15, the second one around the y is 4, and the last one around the c is 36. All in foot-pounds because the distances are in feet and the force is in pounds. Final answers. So that was it for the first one. Now we need to do the second problem, which they want you to find the moment about the line of action that goes from A to C. So in order to find this moment along AC, you need to find unit vector AC, and that's the cross product between from A to B. Which is this vector cross F. So first we need to find the points involved. A is at the origin, C is at 4 in the I plus 3 in the J plus 0 in the K. So AC is C minus A, but A is the origin, so it's equal to C, which is equal to 4 in the I plus 3 in the J plus 0 in the K. The magnitude of AC is given by the x component square plus the y component square plus the c component square. When you plug in these three values into this formula, you get that it has a magnitude of exactly 5. Then to find the unit vector AC, you divide the vector AC by its own magnitude. So dividing these three values by 5 will give you the unit vector, and it comes out to be 0.8 in the I plus 0.6 in the J plus 0 in the K. So we already have our first vector. We already have our fourth vector because it's given right here. All we need to find is AB, which we found before to be 4 in the I plus 3 in the J minus 2 in the K. Just rewriting it. So the moment along AC is equal to UAC. So UAC is 0.8, 0.6, and 0. Then AB, which is 4, 3, negative 2, and F, which is 4, 12, and negative 3. So you redraw first and second columns. This is 0.8, this is 0.6, 4, 3, 4, 12. You do your positive diagonals, positive, 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 and it's, this one is negative 7.2, 0.6 times negative 2 times 4 is minus 4.8. This is 0, negative diagonals, negative, negative, negative. First one's 0, second one is negative 12 times negative 2 times 0.8 is positive 19.2, and last one is negative, negative 3 times 4 times 0.6 is plus 7.2. Also these two cancel out, cool. So it comes out to be 14.4 foot-pounds, but this is a magnitude. They want it as a Cartesian vector. So you want to know where it's aiming? Well, it's aiming straight down U from A to C. So to find the moment in Cartesian vector form, you gotta multiply the magnitude that we just found, which is this, times UAC. So 14.4 times UAC comes out to be 11.52 in the I, plus 8.64 in the J, plus 0 in the K. Final answer for the moment that F creates about the AC axis in Cartesian vector form, because you know that it acts that way.